Every single second of the day, a modern web server is bombarded by millions of individual data packets. Getting that massive influx of data across the globe is the exclusive domain of the network layer, primarily using the Internet Protocol. IP addresses act like geographic coordinates, mathematically guaranteeing that a packet successfully navigates the physical infrastructure of the Internet and arrives at a specific target machine, known as a host. Look at this network model. The red arrow illustrates logical communication strictly from physical host to host. But arriving at the machine isn't the end. A computer rarely runs just one task at a time. Right now, a single server might be running an email client, a web server, and a background software updater concurrently. The network layer only solves host-to-host delivery. Without a mechanism to sort data once it penetrates the host, incoming packets would be blindly dumped at the server's doorstep, causing immediate system failure as applications scramble to read unrecognizable code. To solve this, network architecture relies on the transport layer. Its specific job is to establish logical communication between individual application processes, closing the gap the network layer leaves open. At the sender's end, this involves a phase called multiplexing. The transport layer gathers raw data chunks from various applications and packages them with special transport headers. This schematic shows multiplexing at the sender. Data from separate processes, P1 and P2, funnels down into a single pipeline. At the destination, the system performs demultiplexing. The transport layer examines the segments, sorting them upward to the correct application. The critical boundary where this handoff occurs is the socket. It operates as the dedicated software doorway between the transport and application layers. So, how does the operating system mathematically determine exactly which socket gets which payload? Accurate demultiplexing is the ultimate safeguard against data corruption. It guarantees your incoming email stream routes directly to the mail client and doesn't overwrite your active web browser session. The operating system derives its routing logic entirely from the metadata packed into the transport header during the multiplexing phase. Here is the standard format for a TCP or UDP segment. The payload sits at the bottom, but the sorting logic is built at the top. Notice this specific 32-bit block. Every segment carries a source port number and a destination port number. A port number is a strict mathematical address permanently assigned to an individual socket within the host machine. If the IP address routes data to the physical building, the port number tells the internal system exactly which apartment mailbox receives the envelope. The operating system continuously reads these incoming packets, pairing the external IP address against the internal port destination. Combining the IP address and the port number creates the exact logic required for true process-level network isolation. To see how this routing is applied under stress, we have to analyze connectionless transport, specifically the User Datagram Protocol, or UDP. UDP is engineered to be fast and lightweight. To route packets efficiently, it executes a rule known as the two-tuple. The two-tuple rule dictates that the operating system checks exactly two variables on an incoming segment, the destination IP address and the destination port. This diagram illustrates a server receiving connectionless data. Focus on the center machine running a process tied to a yellow socket, mathematically mapped to port 6428. Trace the traffic from the computer on the left. It sends a datagram originating from its own port 9157, aimed directly at the server's port 6428. The server accepts it and pushes it up the socket. Now look at the computer on the right. It fires off a completely separate datagram from port 5775, targeting the exact same server port 6428. Because of the two-tuple rule, both distinct streams are routed into the exact same yellow socket. The operating system running UDP completely ignores who sent the packet and which port it originated from. If the destination matches, it passes through. Under this architecture, UDP acts as a single shared intake funnel. It blindly aggregates any network traffic targeting that specific destination port. Because UDP is a no-frills extension of standard IP, this two-tuple approach minimizes overhead on the server. The cost is that the application itself must manually sort out which data came from which user, trading organizational complexity for raw speed. The mathematics change entirely when we evaluate connection-oriented transport. Transmission Control Protocol, or TCP, requires strict reliability and perfectly ordered data streams. To guarantee this reliability, TCP abandons UDP's shared funnel architecture. Instead, TCP deploys the 4-tuple rule. It identifies sockets by strictly checking the source IP, the source port, the destination IP, and the destination port. Imagine a server receiving 3 distinct data segments. Under standard UDP rules, they look identical, aimed precisely at the same destination IP and destination port 80. But TCP demands a deeper analysis of the metadata. Checking the full 4-tuple reveals that these segments actually originated from 3 completely different source IPs and source ports. Reacting to this, the server's operating system does not lump them together. It immediately spawns 3 entirely separate, dedicated sockets, routing one segment strictly to each. This is the absolute rule of TCP. If any single variable among those 4-tuple values changes, the operating system routes the segment to a completely different, newly generated socket. TCP's 4-tuple architecture mathematically guarantees isolated data streams. One client's payload can never physically cross into another client's dedicated connection pipeline. We can see the true efficiency of this architecture when analyzing a modern web server handling global traffic. There is a common misconception that routing web traffic to port 80 forces millions of global users into one single congested server connection. In reality, when thousands of users connect to a web server on port 80, the 4-tuple rule prevents bottlenecks. It forces the operating system to simultaneously manage thousands of unique, individualized sockets. A single destination point logically splits into thousands of parallel, isolated processing pathways. This architecture easily manages non-persistent web requests. The server rapidly creates, utilizes, and destroys these dedicated sockets in mere milliseconds as users click through pages. The contrast between the two protocols is total. UDP operates as a singular, open funnel, maximizing throughput, while TCP generates massive, highly organized parallel threads. Port numbers alone do not define unique connections. The underlying tuple logic of the chosen protocol dictates the entire architecture of the session. The transport layer's multiplexing rules are exactly what allow modern hardware to scale. It is the architectural foundation that lets a server balance millions of simultaneous, secure global sessions without collapsing into chaos.